So, in the last class, we had a discussion about the feedback networks, or basically, we are focusing on degenerative feedback circuits, or in short, negative feedback circuits. And we had a lot of discussion about the important properties when we had this feedback circuit. And one of the so all of these important properties came into picture just because at an expense of reducing the gain of the circuit. And we also spoke about this loop gain, which is the product of the open loop transfer function times that of the feedback factor beta. Now, today we'll be focusing on those four basic feedback topologies by making use of this basic op amps or basic amplifiers, and these basic amplifiers can be categorized under four different categories. The first one being the voltage amplifiers, the second one being the current amplifiers, transconductance and transresistance amplifiers, and in short, the input and output of these amplifiers are being specified. Okay, so with that as a base, let me define the voltage amplifiers or the basic amplifiers configurations, and let me begin with the voltage amplifier. So this is just the ideal amplifier configurations. Okay, yeah. So today let us begin with this voltage amplifier. So in the case of a voltage amplifier, and I'm talking about the basic amplifier, so it is the open loop amplifier is what I'm talking. So please bear that in your mind. And so with that, uh, for so this is an amplifier that takes an input, which is a voltage, and that produces an output, which is again a voltage. Okay, so one could characterize this voltage amplifier, which I will just write it as A, uh, could be, or the internal structure of this voltage amplifier being an ideal circuit could be modeled as something like a voltage that we are feeding here as Vi. Okay, and we will have a voltage controlled voltage source, and that could be modeled with this diamond shaped symbol, and I have a gain, or the output voltage is basically Vo, which is defined as the gain times that of the input voltage. Okay, so this is the ideal model, and in case if there is a non-ideality, then we will be ending up adding some sort of resistance along, at the input as well as the output. Okay, so let me just quickly even put that, but today's focus will be on dealing with this ideal structure, but in the coming classes we will just see, like, uh, we'll just try to incorporate all these non-idealities, and then later we'll discuss about it. Okay, so in case if we want to have a non-ideal condition across this structure, then in short there will be a resistance Ri. Okay, so this is the non-ideal basic amplifier, and even this voltage source will also have a non-ideal resistor, but this resistor will be in series as R naught. Okay, and again one could have this V naught to be defined something like this. Yeah, so these are the basic amplifiers ideal model as well as non-ideal model, and similarly let me try to bring the structures of other amplifiers, the next one being the current amplifier. So in the case of a current amplifier, the amplifier will take in a current and splits out a current as well. So I will have both input and output as currents, and this is the symbolic representation. And let me try to draw this internal block diagram of this amplifier, okay, which is the current amplifier. And as we know that ideally we want to pull out all the input currents into the amplifier. The best way to draw all the currents is by having a short circuit rather than open circuit like a voltage amplifier. So in this case, if at all, if I don't have any resistance through this particular path, whatever the current that comes in as II would then be brought inside, okay. And we also need a kind of current controlled current source component which acts as a gain medium, and that in turn defines an output current which is I naught, okay. So this is the ideal structure. The non ideal structure will include again some set of resistances. uh, so in short, the output current source will have resistance R naught here, and even this input current will have some sort of resistance. I guess it's supposed to be in series, I guess. I'm not pretty sure about this current flow, but okay. So probably this non-ideal current amplifier notation. I'm not pretty sure about this input component, but I'm pretty sure about this output component here, that is the non-ideal condition at the output. But let me just bring out this particular model when we deal in the next class. Okay, so as of now, I have just uh, used an input resistance component here, but the exact representation I will just check it in the next class. But as of now, we'll just hold this model as a model for a non-ideal current amplifier. The next one is our trans conductance amplifier. So in the case of a trans conductance amplifier, the input is a voltage and the output is basically a current, right? So the amplifier reads in a voltage which we modeled as Vi, and it provides an output current which has been modeled as I naught here. Okay. So the way by which an ideal structure would have is that uh, if at all, if you want to read all the voltage through this amplifier, the input impedance of this voltage component supposed to be an open circuit such that you can extract all the information of this Vi that is uh, appearing towards the input of your amplifier. Okay. So the ideal way of modeling this input voltage, the transconductance, is by having an open circuit path. And again, in order to generate a current component, we need a gain times that of Vi. So this is something like a voltage controlled current source, and this is how I could re-represent the ideal model of this amplifier of transconductance. Okay. So again, I think let me just let me not draw the non-ideal model, but as of now I'll just go ahead with the ideal model for today's discussion. And the later one is about the trans resistance amplifier. So for the trans resistance amplifier, the input is a current and the output is a voltage component. So due to which symbolically I could draw the amplifier with a voltage at the output as V naught, but the input current is modeled with a signal II. And in order to draw all the current, ideally the input impedance of this amplifier of trans resistance amplifier is supposed to be 0. So due to which I can draw all the current by passing this current through a short circuit. So have this II, and we need what is known as current controlled voltage source here, which depends on the current flow through the input port, and this in turn provides us an output voltage V naught. Okay, so hope that all these ideal model of this basic amplifier is clear. So now to this model we just want to add the feedback circuit along with the input source component. So this input source can be either a voltage source or it can be a current source depending on the type of amplifier that we are discussing. Okay, so let me just begin with the discussion of this voltage amplifier and try to see how does it impacts, and let us look across a few of the models that would help us to quickly identify the feedback network and what type of sampling and mixing is happening. Okay, so let me just give a brief overview of what I'm really uh, talking here. So basically there is a feedback network beta. This feedback network beta in general samples the output, okay, samples the output signal and mixes the fraction of this output to the input. Okay, so it basically mixes the feedback signal along with the input source. So it generally mixes. Okay, so whenever I say sample, I am talking about the path from the output of the open loop amplifier to the input of the feedback network, and whenever I am talking about a mixing, it is the mixture of both the input source component along with the feedback signal component, and that is what we really mean by this mixing. Okay, so let me begin with this discussion of sampling and mixing, and let us start with this voltage amplifier first. So let me write it as voltage amplifier. So today class we will be discussing only on these models only with respect to ideal basic amplifier. Okay, so we'll just hold today's session only with the discussion of the ideal basic model. Whenever we have this ideal model, uh, there is one important advantage over the discussion. So having this ideal basic amplifier as our model will in general will not impact our gain expressions or the input output expressions uh, due to the loading effect of feedback network as well as the loading effect of the source component. Okay, so whenever we have this ideal basic amplifier, no loading effect uh, is required. Okay, there is no loading effect on these amplifiers. Okay, so the calculation becomes much more simpler, and that is how I can cover all the amplifiers in a single stretch. But otherwise this requires a lot of analysis how the networks like beta network or the feedback network along with the source uh, signals, okay, even they will have some sort of loading impact on these amplifiers. Okay, so no such effects will not be considered, no need to be considered basically when we deal with this basic ideal op amp model or basic ideal amplifier model. Okay, yeah. So in this case the voltage amplifier is basically a voltage controlled voltage source, and that is what we have modeled earlier, right? And we generally want this input to be as high as possible. In general, ideally we want this input to be infinity, and R out of this basic amplifier supposed to be equal to 0. Okay, so this is the ideal model of this basic amplifier A, okay, or open loop amplifier A. So both are one of the same. And since the input signal source is a voltage source, one could actually model this voltage source in terms of Thevenin's equivalent circuit. Okay. Yeah. So what I really mean by this particular statement of Thevenin equivalent source is that if at all, if you have any voltage source, this voltage source in short will have a resistance, a source resistance associated with it, and one could model that as a kind of voltage in series with that resistance Rs. Okay, and that is what we mean by this Thevenin's equivalent resistance model. Okay, now let us begin with the type of feedback topology that we really needed, and let me model that with a kind of picture. So let us assume that we have this basic amplifier, which is an ideal model, basic voltage amplifier, and we know that the input is supposed to be Vi, and the output is basically a Vo, and let us assume that there is a kind of load that is being attached to this circuit with a load resistance of RL, and the drop across this load is modeled as V naught. Okay, and we also have a source which is Vs, and which is a voltage source, and this voltage source, if at all, if it has kind of resistance, the source resistance that can be added in series with it. Okay, and that is what we mean by this Thevenin's equivalent circuit. Now we need a feedback circuit that actually samples the voltage at the output and feeds the input or mixes this feedback signal Vf as a kind of voltage uh, in series with this Vi. Okay, so what I really mean is that let us begin with the discussion of the voltage sampling. Now, the voltage sampling is something, is a phenomenon that happens. Say for example, you have a voltmeter, and the way that this voltmeter is connected to a circuit to read out the voltage across any circuit is by tapping both the terminals across the load. Am I right? So, so you have to measure, or you take the two probes and put it across the load in order to measure the voltage across it. Okay, so in a way that I have to put some two probes in this particular way, and then I have to feed them to this feedback network. Okay, so in this case, this type of structure will ensure that we are trying to read a voltage out of it, and the type of input that I am feeding here would be the same Vo. Okay, so this is how I could measure a voltage. So voltage sampling could be thought of as a kind of voltmeter trying to read a voltage across a particular load. Okay. Now that this volt has to be connected in series. So now in the sense I have to mix this feedback networks output, and the output of this will also be in terms of a voltage. Okay, and let me label that voltage as Vf. Now this has to be fed along with this Vi such that I have to put them in this particular way. Okay, so that what is happening here is that the the source voltage Vs is nothing but it's a summation of Vi plus Vf, and this is the type of equation that we were discussing even at the beginning. Okay, so we want to mix them such that the difference in this Vs minus Vf will define this Vi. Okay, yeah. So I hope that I'm not confusing. So in this case, we are mixing this voltage with this path or with this type of connection as a kind of series connection. You could able to see that there are two batteries that are connected in series, where the polarity of plus symbol is at the top, and then there is a negative sign, and then again we add them with a positive polarity with a negative sign. Okay, so these type of connection is known as a series connection, or connecting two batteries in series, right? In order to, if at all, if you have a torch, you will have this kind of voltage connection in order to create a potential of required voltage. Okay, say for example 1.5 and 1.5 volt, then these two will appear in series in order to create a 3 volt in order to light up your bulb. Okay, the same way this could be thought of. So the type of network that I have here, in order to read this, or in order to sample the output voltage, the type of connection or the type of connection that is being made is known as a shunt connection, because you could able to see that these are connected in shunt, okay, or in parallel to the load resistance, okay, whereas the feedback signal is fed to the input or mixed with the input as in terms of a series connection. Okay, so the type of connection that we have made with this type of connection is known as a series. Okay, yeah, in few textbooks there is always a confusion between the type of notation that we generally follow. Okay, um, so in short, I could say that this type of feedback that we have, or the topology that we have, has a kind of connection which is known as voltage mixing and voltage sampling. Okay. So the mixing part is basically with respect to the input, and sampling part is with respect to the output, and this is termed as the feedback topology. Okay. Or there is also one more way by which I can tell the same sort of feedback connection as something like series shunt feedback. So the type of feedback that we have here is again, input is basically a series connection, the output is basically a shunt connection, right? So it is labeled as series shunt feedback. Is that is clear? So this is all with respect to a specific book, which is not Razavi, but I forgot the name, but I will let you know about this. Okay, so each author follows a different way. So sometimes people used to refer the output first, followed by the input, as the type of feedback topology, as well as the type of feedback networks. Okay, so but what we would follow is something like input followed by an output is what we would follow. Clear? So this is the type of network that we have, and let us quickly look into some set of examples and see whether we could really tell whether the type of feedback that I have is a voltage mixing, voltage sampling feedback topology, or other type of topologies. Okay, so let me just quickly give some sort of examples, and we'll not discuss much today. So all the discussions and calculations will be done in the next class. So yeah, so now can you identify what type of amplifier it is? So basically this is something known as a non-inverting amplifier, but what type of feedback that has been used here, and what is that we are sampling, and what is that we are trying to mix it, and that is where we could able to identify whether it's uh, a voltage amplifier with a voltage, or with a series shunt feedback or something else, right? So basically we could be able to see that we have a kind of circuit where we don't have any source resistance as of now. The RS is not completely there, so we have an ideal source component without any resistance, and that is being fed directly here. And let us try to fix these potentials. Okay, so we know from the basic structure that the input of this basic amplifier is supposed to be a Vi. Now let us see whether we could identify that component. So in this case, this triangle or the op amp that I have here basically represents my open loop amplifier or the basic amplifier. Now the input of that is supposed to be Vi. Okay. Now we know that this Vs is supposed to be a summation of Vi plus some feedback potential in order to create uh, the the series shunt feedback network. Okay. Now let us identify where exactly our feedback network lies. So clearly we could be able to see that the combination of R1 and R2 creates this feedback network, and clearly the input of this feedback network is basically trying to sample a voltage with respect to the ground, right. So clearly you could be able to see that there is a direct point that connects uh, the V naught to the input of the feedback network. Okay, so this is where we call it as a voltage sampling through this feedback network. And how are we connecting this back in terms of VF? Okay, so where exactly the VF appears? So if you carefully look here, the VF is nothing but it appears as a drop across this resistance R1. Okay. And as you could clearly see that this Vs that I have here is basically splits across as a kind of voltage drop across the input of our amplifier A plus the drop across the resistance R1. Okay. So in a way we could see that this network of R1 and R2 basically creates what is known as series shunt feedback network. Okay. And again, to ascertain whether this type of feedback network that I have is basically a negative feedback or not, first of all let us try to check whether this is a negative feedback network or not, right. So let us try to increase this voltage Vs. So when we try to increase this voltage Vs, what happens is that our V naught will also rise up just because of this increase in the Vs will obviously try to increase the value of Vi as well, and in short our V naught will also rise up. And as I said earlier, the Vf will also have to have the same uh, direction. If there is a rise in the value of Vs, then Vf will also have to rise in the same direction. Okay, and that is how we can subtract it from the Vs in order to create a small potential of Vi across this uh, amplifier. Okay, so now let us go for the second example, and this is just to identify the type of feedback, and we will be really solving all these problems later on in the coming classes. But today it is just the overview of all the type of feedbacks. Let me just try to draw, and this let it be Q2 and this is RD2, and we have a V naught here, and then we have this Vs with plus and minus. Yeah, so this is the type of network that I have, and along with this feedback signal that is being fed here. Okay, so now that the very first basic thing is that we need to identify our feedback network. So the identification of this feedback network appears over here. Okay, so this is our feedback network, and let us try to identify whatever feedback network it is. Is it a series shunt feedback or is it something else, right? So in this case the input to this feedback network is basically samples or directly reads the output voltage V naught, right? So the type of connection that I have made is basically known as a shunt, which reads a voltage. Okay, but how is that is being fed back to the input? So as you could able to clearly see, in the place of Vi, what I have here is my VGS. Okay, so the VGS of Q1 appears as Vi in our case, and again the Vf appears as a drop across this resistance R1 as Vf. So one could see that this voltage source Vs is nothing but is a series connection of Vi and Vf. So which means that we have a series connection at the input. So the type of feedback network that we have is a series shunt feedback. Okay, so hope that you're clear with it. And again, in order to check whether uh, the feedback network is actually a negative feedback, one could again start with the discussion of Vs when you rise it. What happens is that the current through this Q1 will also rise up. Okay, and when the current rises, what happens is that the drain potential which I'll write it as VD1, will start dropping just because VD1 is defined as VDD minus the ID1 times that of RD1. So when this ID term rises up, the VD will generally falls down, and due to which our VD1 will drop. And when it drops, what happens is that the V naught, which is again defined as VDD minus ID2 times that of RD2. So just because our VD2 is fed as a gate input to our Q2 structure, the ID2 will again drop, and due to which our V naught will rise up. Okay, and as you could see that the rise in this V naught is read through this VF as a voltage divider. Okay, so VF is nothing but uh, R1 divided by R1 plus R2 into V naught. So when this V naught rises, obviously the VF will also rise. So both these signals of Vs and Vf are rising at the same time, due to which the type of feedback network that we have is basically termed as negative feedback. Okay. So finally, there is a last example covering up the voltage amplifier is a kind of bit tricky. So let us see whether you could able to see. You could identify the type of network that we have. Yeah. So now let us try to identify what type of feedback network is this. Uh, so first of all, the feedback network is just this R1 and R2 combination is basically our feedback network. Now the next thing is that we need to see what has been sampled as an input to this feedback network. So generally in this case we are sampling directly the input signal V naught. The type of sampling that we are doing is basically a shunt, just because the shunt will help us to read a voltage, and that is what we are doing it. But what type of mixing is happening across this network and fed as a kind of VF signal to the Vs. Okay, so here one could see that this Vs could be returned as Vi. So where Vi is again falling as the drop across the source and gate potential. Okay, and Vf appears as a drop across the resistance R1. So clearly there is a kind of voltage mixing that is happening here, and whenever we want to make a voltage mixing, then we need what is known as a series connection at the input. Okay, so in general used for mixing a voltage, okay, the series connection. So the type of feedback network that we have is a series shunt feedback. So let us jump onto the second type of amplifier, which is the current amplifier. Now in this case, since the input signal is uh, a current, uh, the signal source can be represented as by its Norton equivalent circuit. Now this is a bit different when we had the input signal being a voltage. Okay, so in this case the input source is basically a current, and when we have a current as our input signal source, then one could use a Norton equivalent circuit model. Okay, so what it really means is that the input current could be modeled with a kind of a current I in or IS, and the source resistance will appear in parallel to it, and this is what we mean by this Norton equivalent circuit. Okay, whereas if we had, as earlier, if this input voltage source, so if this signal source is a voltage, then it has been modeled as a kind of Thevenin's equivalent circuit. Okay. Yeah. So now anyhow we are just dealing with this current amplifier. We know that it basically reads in a current and spits out a current. Okay. So let me just draw the model of it, and let me just draw along with this component itself. I have a basic amplifier, which is a current amplifier, and the ideal behavior or the ideal model is already been shown. So you can actually refer back, and what we are feeding in and tapping out is all the current. So the input is II, and since because there is a short circuit here, the same current would loop around. Okay, the current always goes in a loop, and it also reads in a current. So let me just have a current, and let us also include a load, which is the ideal model, a non-ideal model across the or outside the uh, basic amplifier. Okay, so these non-ideal models of sources and the loads will not impact the gain expression until otherwise the basic amplifier uh, is an ideal amplifier. Okay, so in case if this basic amplifier is a non-ideal one, then these components would then impact the gain expression and many things. So those things we will discuss in the next class, but as of now today we just our primary focus is on the ideal model of this basic amplifier. Okay, so with that being said, this is how the structure is, and we also have this feedback network being applied, and this feedback network has to sample in a current. Just because the basic amplifier uh, spits out a current, we want to sample that particular current. Now the way that one could sample, or one could think about the sampling of a current, is by thinking about a current meter. Okay, so in a way, say for example you just want to measure some sort of current, what you generally do is that you just apply your current meter through a kind of series connection. So which what we really mean is that if at all if I have a ammeter, you put them and then use something like this, and the current flow through the circuit or wire is being read like this. Okay, so the same wire is fed in and fed out. Okay, it is not, whereas the voltmeter has a different kind of connection where the voltmeter is measured across two wires. Okay, that is how the voltmeter is generally used for the measurement, whereas the current meter or the ammeter is been fixed along a single wire. Okay, so now that we just want to have this kind of structure, I just want to pass this current to flow through this network and then pass it out. So in a way, I have to read in this current and then split out this current to this network. Okay, so the current actually goes in the forward path and then it comes out as I naught and goes like this, and the same current I naught would go on the other hand. Okay. So in this case I am going to assume that even the feedback network that I have is an ideal feedback network. It does not um, take off any output current into it. Okay. So that is how I have modeled this, both these basic amplifier as well as the feedback amplifier. So now the way that it has been mixed up with the current being mixed with along with the input is by putting them in a kind of series. Okay, so we know that the current Is supposed to be a summation of Is plus If, and this is what we wanted actually. Now already from this Is a current component is been going to the input of our basic amplifier as II. Now the way that I can draw the current out of this is by tapping the node something like this. Okay, so I have to have this tap and put that, and then again tap this network in order to put it. So what is happening is that at this particular point the current Is splits into two components, and this particular component is nothing but my IF, okay, and the one that goes towards the amplifier, basic amplifier, is our II, and that is how I used to mix our current, okay, and this current is fed inside this output of the feedback network and it's been pulled out, such that again when this current component that is coming out of this basic amplifier would then be again mixed up in order to create the current IS, okay. So hope that this connection is clear, okay. Now when I look for carefully across the type of network or the connection that I have made at the input, you could see that it's a kind of shunt connection, okay. So this is known as a shunt connection, but the type of output connection that we have made is known as a series connection, okay. So in general, a series connection at the output or with respect to sampling defines what is known as or measures what is known as the current, whereas the shunt connection across the input or mixing will generally help us to mix a current component, okay. So this is for sampling uh, for a series and shunt for mixing it, okay. So hope that you have to be clear with these concepts, and I'm hoping that you are clear with these concepts, okay. So let me just have a quick example. I will not spend much time as we don't have much time to do a lot of exercise and discuss about each of these one. So I'll just quickly bring a quick example, and with that example we'll just move on to the next one. So I have a resistance RD and then Q1, we have a VI, a VG, so Q2, Q1, and there is RF. Yeah. So yeah, so this is the circuit, and we just basically have to identify um, the feedback network out of this. Okay, so the very first thing is the identification of the feedback network, and many a time even this source component will not be given as IS. Okay, so sometimes we try to tend you to think in a different way. So we just try to model this IS in terms of a voltage component. So even in that case, just by looking at the type of feedback network, one could uh, redraw this uh, voltage source as a current source, and then uh, you have to analyze the circuit. We will do all such problems in the latest classes, but as of now let us try to figure out our feedback network. So in this case clearly there is no visibility of having a node as V0, okay, and let us assume that we have a resistor RL, and the output of this resistor RL, because we know that across Q2 the current ID would flow, and that current when it flows through this resistive load RL, it creates a voltage, and let us label that as a V0. So clearly my feedback network is only the combination of this RF and RM, okay, and and the input to this feedback network is not directly measuring the voltage, okay. So I'm not feeding this V0 as an input to this feedback network, but rather I'm passing through this resistive RL. So which means that we are the type of sampling that we are doing is basically a current, okay. Hope that it is clear. So in case if I had Q2 here, and then say for example I had a kind of resistance, and if at all if this node is labeled as a V0 and the feedback network is trying to measure directly from here, then we are sampling a kind of voltage, okay. But in this case the V naught is not represented here, but rather it has been taken out here, just because this resistance is modeled as a load resistance. The top potential of this node is taken as V naught. Okay, the top terminal of the load resistance is taken is measured as a kind of voltage. Okay, but many a time even that will not be shown in this figure. Okay, so in that case, clearly one could see that we are not exactly measuring the voltage, but rather we are sampling a current through this load. Okay, so the hope I'm if you're not clear, we'll just discuss in the Zoom, but as of now, we'll just go ahead with this discussion. So the way that we are sampling is not directly feeding the output voltage as an input, but rather we are passing it through a load or some sort of rescue network, and then we are tapping the signal. So in such case, the measurement that we are making is a current. Okay, and again, when we look back, clearly you could see that there is a current component Is, and this Is could be modeled as one of the current component as II, the other current component as IF. This is our feedback current. Clear? Now, since because the input impedance of this source terminal is pretty small, which is GM1 by GM1, the current can flow through this network. Okay, so basically the type of network that we have is basically what is known as sorry, it's not series, it's basically shunt at the input and series at the output. Okay, yeah. So let us move on to the next one, and which is nothing but the transconductance amplifier. Now, again, the input and output signals has to be clear for this transconductance. So the basically the input signal for the transconductance amplifier is a voltage, and the output signal of this transconductance amplifier is a current. Okay, so now clearly based on the first two phenomena, one could uh, really say what type of model, what type of feedback topology that is really required. Okay, so in the first case, since the input is a voltage, the type of mixing that I need to do by using this feedback network is nothing but it's a voltage mixing. And since the output is a current, we want to sample a current. Okay, so it's a current sampling is what we want to do. Now let me write this basic transconductance or GM amplifier, or let me write it as capital GM, and let us have a voltage source which is Vs, and there is a kind of resistance, source resistance Rs, and let us leave this as it is, and we also have a load impedance that is connected. Yeah, so let us have this feedback network, and let us try to analyze what type of connection is required for sampling the current, and what type of connection is required for mixing a voltage. So since because we want to sample a current, as I said, we have to think as a kind of ammeter, and this ammeter has to pass through the current by taking a single wire. So in this case, the single wire that at which I'm just going to sample the current is by passing this and these two connections. Okay, so the type of connection that I have created over here is known as a series. Now let us try to mix a voltage. So as we know that the voltage drop across this basic amplifier is labeled as Vi, and now that I just want to add a voltage Vf in series with this Vi, so which means that I have to add this Vf, where Vf is generated out of this feedback network, and that has been mixed something like this. Again, when we look here, the type of connection that we have made is a series connection. Okay, so Let me quickly draw only one example for this. Hopefully you will be clear right now. So we have an amplifier, and again there is one more structure Q2. Let me mark this amplifier having a gain of 1, and the input to this is basically a Vs, and there is again a feedback, and there is a resistance Rf. Okay. So now in this case again the type of load that I have is an RL, and we are not tapping the voltage from here. Okay, so what I really mean is that the feedback network has to be first identified. So in this case the feedback network is just the resistance RF, and the input to this is not directly tapped from this particular node where we actually mark that particular node as a voltage, but rather it has been passed through a resistance and then we are measuring it. So in that way whatever we are sampling is basically becomes a current. Okay, so we are sampling a current through the load, and then the drop across this RF will generally creates a voltage as Vf, right. So that voltage will appear in series just because we have Vi with plus and minus, and there is a Vf with plus and minus. Okay. So that is how it is the feedback network RF uh, creates something known as series feedback. Okay. So finally we end up having the last type of amplifier, which is the trans resistance amplifier. So let me quickly model that, and let us have so since in this case the input signal is a current, I use Is and been modeled as something like a Norton's equivalent circuit. So I'll just apply this resistance Rs in parallel with the current source, and then there is an basic trans resistance amplifier, which is an ideal model, and it passes through a load which is RL, and the output of this is generally a voltage, and the input of the amplifier is generally a current, a current II. Yeah. So now let us try to have our feedback network, which is again modeled as a kind of ideal network here, and we know that we want to sample the voltage of this basic amplifier. So the type of connection that I have to make is a shunt connection, just because something like a voltmeter that we have. So let me just sample them. So that we have this voltage appearing across the input of this amplifier. But what suppose we mix is a kind of current. Okay, so we want an IF to be generated out of this feedback network, and this has to be mixed with this IS in order to create the II current, right. So we generally want to have a connection where the IF is being tapped out from here, passes through this network, and it's been released by this feedback network, and it's again fed back to. Okay, yeah. So hope that it is clear from this perspective, and even the current II that is coming out will then reunion with IF in order to create this IS here. Okay, yeah. Now the type of connection that we have across the input is basically a shunt, and the type of connection that we again have across the output is basically a shunt. Okay, so we have a shunt feedback network in this configuration. So let me demonstrate a simple example, and with that we'll end this session. So we have is, and in this case a voltage, and we have a feedback network which is modeled as RF, and clearly you could able to see that this feedback network has an input which directly measures the output voltage. Okay, so the type of sampling that we are doing is a volt. Okay, and the type of mixing that we are doing is a current, just because the current is has to flow in these two paths. Okay, so as if as well as the ii component. Okay, yeah. So with this I will end the session, and I will just forward you the Zoom invitation. You can just come over there for the further queries.